see, should I so for the walkie-talkie? No, it's on. So you're just opening them up?
Is that apropos or what?
Well, you know, we're pretty close to pi age.
Yeah, right. So I don't know if you want to say something about that or whatever.
No, it's all right.
The clock is a little late back there. Maybe I'll go fix that clock in the back.
Oh, it's not bad. It says 56.
Okay, we're all right here, Joe.
All right. Should we just go ahead and start rocking and rolling? It's mostly art. You see, it's our disrespectful people. Oh, yeah, maybe so. Unless there's somebody, is there anybody left outside? Yeah. So let's see. Oh, we got one more. Huh. Okay, so Pedro made it back from the field, and I trust that means we didn't lose anyone in an irrigation ditch or anything. I will say, if you happen to drive around on the field, it's a common experience for Priuses to go into the canal. We've had two so far, and so maybe they need an ultrasonic proximity sensor mounted on the front. Okay, I'll be talking about the ultrasonic sensor. So I hope on the tractor you saw this funny sort of white inverted cone thing with a sensor inside it. That's one brand of ultrasonic sensor. And first thing is to say that these work. And this is actually from a cotton field, and Mike Gore was responsible for coordinating this. And so this is the sensor height measured with the pulsar sensor, and this is manual measurements of plant height, and that was done with essentially a meter stick with barcodes and a barcode code reader. So faster than just looking at a ruler and writing it down, but clearly this sensor is doing a pretty good job. Okay, why measure crop height? Of course, it's interested as a trait per se for things like lodging and for mechanical harvest. Height's a good indicator of overall growth, and it also often reflects key developmental stages, like you get a rapid change in height with bolting, and brassicas can represent the end of height growth, or the end of height growth can indicate your onset of grain filling in cereals. Height obviously relates to canopy architecture, so if you're interested in light interception, it's sort of, maybe a useful covariate. Of course, then you get things like lodging resistance attained by a shorter plant height was an important part of the Green Revolution rice and wheats. And also can be useful as a covariate to enhance interpretation. And for example, reflectance measurements often are biased by differences in plant height. So what are our usual measurements? You could use or your options for measuring height: a meter stick, using a good eye with a meter stick or a barcoded staff. You could try stereoimagery and photogrammetry, so rebuilding the plant with stereo vision. You might image lateral profiles of the, so looking sideways at the crop, or you can use ultrasonic, the proximity sensors. So that's what we'll be looking at right now. Reasons why we like them, that's what we've used successfully. They've proven to be pretty robust, and they're easy to use in the sense to provide electricity, to get data out of them. Some of the cons, there are way too many options, and we're still sorting through which sensors are the best for field work. As we'll see, the response times are slower than we expected, and that softer, irregular targets, and as Pedro mentioned, for example, the wheat, it's got a lot of small surfaces instead of one solid surface, so that's going to reduce the accuracy. Okay, so ultrasonics, they're just using sonar, just like a bat or a dolphin or a submarine. Of course, these are bats in the air, the others are underwater. It emits a sound pulse. It listens for the echo. It measures the time delay, and then knowing the speed of sound in whatever medium, in our case, of course, air, you can calculate the distance. And so for an example, if it was 0.02 seconds, then you get the distance, 0.5 times 0.02 times the speed of the speed of sound in air, you get 3.46 meters. Let's just mention there's some very fancy uses such as towing of a side scanning sonar to map the bottom of the ocean. So the speed of sound, some other things are useful to keep in mind. It increases about 1% per 5 degrees Celsius, so there might have a little bit of bias depending on air temperature. That'd be so a centimeter for 1 meter, 1 meter distance, so could bias your results slightly. And there's a very small effect of atmospheric humidity, and I think that can safely be ignored. At higher frequencies, you get better reflection off of small objects, so you might look for an ultrasonic sensor that works at a higher rather than a lower sensor. But the higher frequencies lose power faster, so there's a trade-off there. The beam strength from a point decreases as the inverse of the distance squared. So like a lot of the sensors are optimized to put out a much more cylindrical signal. The width of the acoustic beam decreases with the transducer diameter, so you'll see a metal, sort of a metal end plate on some of our sensors, and the bigger it is, the narrower the beam you'd get. Oops, apologize. And the target characteristics are crucial. You're going to get the best reflection from a hard, flat surface, and of course crop canopies then are challenging, they're softer, and you've got multiple reflecting surfaces at different angles. And I should mention also you're moving, and that's going to complicate things a little bit more. Okay, and I mentioned that one of our problems is figuring out which sensor to work with. There's so many options out there. These are all just from one company, and they're optimized for different environments, different levels of sensitivity. Okay, we've done some testing. So in this case, we compared 4 brands, and of course, as an employee of USDA, this is not to recommend anything. This is just to say that these are ones that we use. So we put them on our cart, which I think you may have seen in the background, and Matt Conley will be demonstrating the cart in the afternoon. We put 4 of them on and ran through various tests, and we'll compare work in the lab with static targets and then work in the field. Okay, so static, we see these things are spectacularly good on a hard static target. So this is 31 millimeters, so what, like inch and a quarter square steel bar, and this data that Matt got, just fantastic. And then you get down here, if you're too close, you're within the or you're outside of the range of the working distance. Obviously, it falls off if you get too far away, but there's also a problem getting too close. So the data falls off there. But if you work in the recommended working distance and you've got a good target, it's just beautiful. Then if we try to softer target a piece of artificial turf with no motion, still very good. And then we go out to the field. So here's the pulsar. And so I should explain, this was an experiment with a moisture gradient. So this is actually excess moisture and actually perhaps a little bit of inhibition of growth, then optimal moisture, and then going down to low moisture just a near lethal drought stress for wheat. And this is just a single strip along this gradient. And so what you're seeing is that so these are hand measurements, which are really looking to see the highest point in the canopy. And we instead, with the sensors, we're getting this wide range. And then as we get down here, it looks like it's beginning to pick up the soil. So that looks pretty good. And I should also mention we can fit quantiles. And so this, I think, is the 95th quantile, 75th, and 50th percent quantile. And so we think we could use the quantiles to analyze the variability in height at different levels of water stress through the canopy. But it looks pretty promising. But there was one thing, we could see these funny little chains, and if you zoom in, what you see is that the sensor seems to have a problem. We were logging at 5 hertz, and what was happening is that it's not able to re-estimate the distance fast enough, so it just continues to put out the last distance that was able to calculate. So we really have we're logging at 5 hertz, but it looks like the pulsar sensor actually responds at a slower rate than that. And we checked with the manufacturers, and they said, yeah, roughly 2 hertz. Okay, so let's see. Okay, manual height, honey. Okay, so this is a different sensor, still the same sort of general response. Here we got a different thing, though. We were getting long chains, and apparently with this sensor, when it can't calculate the height, it just holds the last height that it had calculated. So, if you go back, it looks pretty good up here, but then you get down here and you start to get these chains. So that's a little iffy, and we'd like something that performs better than that. So again, when the sensor fails to obtain a height, it holds the last valid distance. Okay, so let's look through some of the characteristics. If you're looking at these sensors, you've got the beam pattern, minimum working distance, a maximum range, and I would argue these are probably optimistic for crops. The response time, as we saw, the pulsar seems to be as slow as 2 hertz, so that'd be twice a second. And if you're going, if you're going about a meter a second through a field, that means you'd only be getting 2 readings per meter, and I'd like to get something better. A lot of differences in the input voltage and the way the output is provided. Could be done as a current, a voltage, or a duration. The packaging. A lot of the sensors, fortunately, are packaged for harsh environments, and as Pedro mentioned, they're often used in industrial settings for measuring the heights of liquids. They're used over sewage ponds, so they're good for outdoor rugged environments. We see differences in cabling. Some of them don't come with cables. Last year, one of the trainees, or actually it wasn't one of the trainees, but it was somebody we were working with, sent us an email at one point saying, gee, I've got these sensors. This is the pulsar, or the Maxbotic sensor. It says he never soldered anything before. And as a result, we're going to have an option for people who want to learn a little bit about soldering in the workshop this year. Okay, and more complex traits. There's a lot there that's not very clear in the literature. They're often doing auto-calibrations. Some of them reduce the strength of the signal when they're working at close ranges, and I think this is to prevent echo problems. There's a compensation for the target size. Some of them have temperature compensation, but it's based on the temperature of the housing. And you can imagine if you've got a housing out there getting heated up in the sun, it might be way hotter than the air temperature, so that compensation might actually be a bad thing. And then there's variation in the sensitivity. And so if you go in the spec sheet, you can get a lot of information. This again for a Maxbotic sensor, showing how the beam, their vision of the beam. So here, say it's a minimum working distance of about 30 centimeters on these, going out to about 1.5 meters, and it depends on the input voltage, in this case, that you provide, and so on. And again, to emphasize, what they're actually doing is, a leaf doesn't provide a single, clear peak. So this is the burst sound from a sensor, and this is what it's hearing as it reflects off of different sensors. And this is why there's a lot of signal processing to try and figure out what's actually the target. And I might mention also, it's a question of can we analyze this signal to indicate a lot more about canopy architecture. And that would be sort of the second generation analysis of ultrasonic sensors. Now, right now, we're just getting an approximation of a target distance, but it might be more meaningful to pick this apart. But that gets us into a much more complicated level of signal processing. Okay, again, on data analysis, the quantiles look promising. They're possible indicator of canopy architecture. The sensors work. The usefulness may vary with the crop type. Don't just go out there and buy the first sensor you see. Working distance, refresh rate, sensitivity are all issues. And here we're interested in testing more sensors and following up with the quantile and canopy structure issue, and perhaps also looking at the best approach for temperature compensation. Some of the sensors you can essentially configure it without any temperature compensation. Okay, I got some questions for discussion. I did want to say that in the lecture notes, there's a table with the comparison of some of the different sensors. So whichever lecture number that is. So if you want to get an idea of the variation, that's there. So I love this. This is when I actually get to ask you questions. What happens if I had 5 sensors going at once, beep, 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 down the field? Any guesses? Crosstalk, yeah. So at least the Maxbotic sensors are set up so they can be triggered. You can trigger 5 of them, or however many you want to at once, and it resets the cycle. But we actually haven't tried that yet, but it's an interesting question. Yeah? Oh, okay, yeah, okay. So the question was, have you tried with different transmission source? And the answer is no. You could build one. You could build a system on your own, yeah, that had say a whole lot of sensors and just 1 or 2 sources of sound. In fact, there's one engineer who said, basically he builds these from scratch. And of course, they all say, oh, it's only $20 of components, but it's knowing how to put it together and making it field robust is another story. But yes, in theory, there could be some issues with crosstalk. That said, at least the pulsar with 4 of them has worked quite well. I'm not aware that we've seen any signs of crosstalk issues. The pulsars worked well in that sense. So, okay. Okay, and so my second question, what would be the best temperature to use to correct for the, there should be a percent, anyway, for the error of temperature on the speed of sound. You've got a sensor temperature. The IRT would give you a canopy temperature. Any guesses? Any thoughts? I would like some average air temperature, over the path. So. And again, the Carthan mat will demonstrate, does it have the thermocouple hanging down? Yes, okay, so we're at least grabbing air temperature as we go through the field. I think that about covers it on ultrasonics on my part. Are there questions? Yeah, Jorge.
Thank you. We're looking at the bounces. Some sensors have the ability to use the first bounce versus the strongest.
Right.
It seemed like you were using the strongest. I was wondering why doing that versus the first one.
Okay, so actually we actually have, this is just off of the Maxbotic page. We actually haven't diagnosed on our sensors, and in fact I think a lot of them we wouldn't, without taking one apart, we wouldn't be able to access this. Although one of the Maxbotic sensors does allow you to access, so this is what we call the analog signal, but you have to record at a very high frequency. Pedro, your comment?
Yeah, I just have one comment related to that question. Is that with the pulsar, there is a microcontroller that is looking at the signal strength as it's coming, and internally is making the decision. So it's not a user adjustable setting that you can tweak. Yeah. It's there. Yeah. So you are limited to that, whatever the processor can do for you.
I guess it covers there are some sensors, some sonars that allow you to select 2 modes. They have 2 modes of operation: strongest bounce or first bounce.
Okay.
And my gut is that what you'll want is the first bounce, assuming that's top of the canopy, which is what you're reminding me.
Okay, yeah.
And if I saw your graphs correctly, it seemed like the manual measures were higher plants.
Yeah.
That might be part of what is going on, that they're getting this, where the canopy gets dense as opposed to the first
go back.
highest point, which is what,
Yeah, so these presumably we were measuring height as to the top of the spike, so we're getting, the tallest of the tallest. So yeah. I should say, for example, the Max Botic, we haven't had a chance to do a side-by-side test in the field yet, but in discussions with technical support for Max Botic, they said, oh, well, the sensor you have probably is looking for too hard of a target, and so they recommended a sensor that's optimized for snow. And you can imagine, so these, and I should mention, some of them are used to measure snow depth in weather stations. And so that's something else that we want to look at. And also, I think, in theory, the pulsar can be tuned, right? It has a lot of settings, but we haven't pursued that yet to see if we could optimize it for a particular one. I guess my one question on what Jorge was saying about this is, until we've looked at these signals, we don't know if we might be getting, say, noise from the tractor, putting out, we don't know what kind of high frequency noise we're getting just of the tractor rattling, or if you're getting reflections off the ground, bouncing up or something. So until we've checked it, we don't know for sure. But yeah, I think it's a fair guess we'd be better off at the front of the peak. Yes. Okay, so the question was, what kind of vibration isolation is necessary? Pedro, what are you using?
What I can say in that regard is that vehicles with engines tend to have very low frequency oscillations. So we are really very far away from that causing noise. Or I don't have the numbers to quantify that in a different way. To answer that question,
Is there a slide that shows frequency range that they're using?
Let's see. Do I have? Good question. Wrong way. So the question was whether there's a slide showing the frequency range. I don't think there is, but I think it's in the table I provide. So I can just say the Honeywell and the Pulsar was 160 kilohertz.
It's in, I mean, if you look at the, well, two thoughts. One is that there was one slide that I'm presenting where that particular number is provided. But more general, whatever sensor you want to buy, you are thinking about a good solution, check the data sheet, and that will tell you exactly where it is.
And the Max Botics are 40 kilohertz, I think. 40, yeah, somebody's shaking their head, yes. Well, Allison is. Okay, one more question, or a couple of questions? Yeah, please.
Do you ever have a problem with thermal noise? I guess just operating out in the desert when it gets really hot, or is that never bothered you?
What type of noise? I'm sorry? No. And I can add one more point that Jeff made on crosstalk, the possibility of happening with multiple sensors. One quick solution to that is to have a pipe just going from the sensor towards the canopy. We tried that, and we confirmed that it's not losing any sensitivity, and that keeps it from crosstalk and having a signal bouncing from different area. Did I answer your question?
Okay, another question, yeah.
Yeah, compared to other methods of measuring time, in which situation this ultrasonic sensor would be your left choice, or conversely?
Okay, I don't think we have enough experience yet, but I should mention, so for example, Dale Wilson, who was in the workshop last year, he's working with Maze. He's using an ultrasonic sensor to measure from the distance, or he's trying this to measure from the distance of the bottom of a sideways looking light bar to the ground. And then he's working with Maze, and so he's trying to use, I don't know if it's a laser distance sensor or if it's just something that looks for visible light, attenuated. But I think as you're getting to tall canopies with Maze with lots of spikes, that might not be so good, as we said, like with the brassicas, cotton, different bean crops. It's very, very good. And also I'd say it depends on the stress level, because I think for wheat, if you're well watered, you've got full canopy cover, I think you're going to get perfectly usable data. But if you're doing drought stress and you've got 60% canopy cover and you're seeing ground half the time, so I'd say it's probably not so much. Well, it's both a question of crop and your growing environment. But it's a very timely question, because our next speaker is Andy, who's going to tell us a little bit about LiDAR, which would be sort of the magic solution to eliminate the need for the ultrasonic sensors. Let's see. Let's see. Do you recognize yours? 1120. There you go. And okay.
Well, we hope it's a magic solution, but I'll be brief because our experience with the LiDAR is still fairly new. We do think it's could be the gold standard for canopy architecture, canopy height. But in preparing for this workshop last week, I was humbled because I looked ahead on the road. It was on Chandler Boulevard, and I saw this Chevy Spark with all this clutter on the top of it. And it was a Bing car, and it had a rotating LiDAR on the top of its ski rack. And I thought, boy, we are pikers. They're mapping the whole city of Phoenix with a Chevy Spark LiDAR unit. And it's moving. And we're moving too, but we're moving over a 3-acre field, and they're doing thousands of square miles. So we have a long way to go. But I do have some results. And also I mentioned in the notes, I don't know if it made it to the agenda, but there's some software called Cloud Compare, and I have a data set that you can look at and visualize what our best LiDAR is so far. And if you're not able to do that, I have it on my laptop, so after the talk, you can take a look at that 3D visualization and see what the potential is for LiDAR. So what is it? Obviously, it's a laser ranging distance. It would be the gold standard if we can get it to be reliable and knew how to process it accurately, and I'll show you some of the obstacles to that. It does not, the way we deploy it, it does not look anything like what you see engineering solutions where they put it on a tripod, they put it in your center city plaza, and you can create an AutoCAD drawing with amazing resolution. Plants are not like that. They're much harder to resolve, much harder to quantify. But the goal here is to get leaf area, canopy height, canopy width, maybe leaf angle distribution, because that would be a response to crop water stress. And then, for example, boll counts. We've shown at least once a plant is defoliated that we can get boll counts. So what I like to do in just in a few slides is show you what the basics are for LiDAR, how it works, and how we're analyzing the data. So what it is, essentially, it's a pulse timing device. Speed of light is 3 times 10 to the 8th meters per second. So to measure crop height, you need to be measuring pulses in nanoseconds. It means it has to be a pretty darn good system. There are 4 components to that. It's a laser light source, some optics, detector, and a navigation system, which we use as GPS, RTK, so accurate to about a centimeter. The technology varies widely. If you've got the budget, you can buy stupendous systems. If you have less money, you can spend a $10,000 or something and get what we have, which at least shows the concept of what you can accomplish, but definitely not as good as these more expensive units. If you add motors and mirrors, you can take a single point of the LiDAR as you travel through, and you can scan your world. And so you can sort of like a circular saw, you can scan through the field and get the distance to your crop height as you go through. Data volumes are very large. The mirror is only spinning, say, at 40 hertz. By the time you're done with the data for 4 days of runs, I don't know, Matt, is about over terabytes worth of data. So huge volumes you're not going to process on your Excel spreadsheet. You need to have other solutions for that. Laser power. These laser light sources are generally quite safe, but you need to pay attention to this because there are lasers out there that are harmful. Class 1 or the old system, Class 3A is what we have, meaning that a glancing look at the LiDAR light is no problem, but you don't stare at the thing. So potential field hazard. This is what we have. On the upper left is the LiDAR unit. It's unit at about 12 inches long. It weighs about 5 pounds. The laser unit is all in here. There's a spinning mirror driven by a motor here and an encoder. And that all gets connected into some boxes here. This is our National Instruments box here. This is the high clearance tractor on which it's mounted. And this is the arm extending from the high clearance tractor. So we will have 2 of these units running this summer so we can scan a total of 4 rows. Power is, the power requirements are quite minimal, not a problem. The laser itself is only 8 milliwatts. The power draw for the whole unit is 400 milliamps at 5 volts. The reason you have high data rates is you have up to 200 kilohertz pulse rates with a scan rate of 40 hertz. Wavelength of light. Important consideration if you want to get one of these things. Don't use green or red, or especially red. And these are less expensive lasers are red, but plants don't reflect much in red. What you want is a near infrared, and ours is 780 nanometers. Platform travel speed is totally dependent on how quickly you're able to collect the data and your logging system. Walking speed is the fastest. Navigation, GPS RTK at 5 hertz. We've just acquired, and people up front here, Aaron and Matt, have been testing inertial nav unit, which is a very nifty thing that has accelerations and Kalman filter for navigation correction. Data analysis. Well, you have to get down and do Fortran or C coding here because the volumes are just way beyond anything you can do for scripting languages. We have C++ and C both, where we merge the GPS data with the LiDAR data. And we format it in what's called PCD format. There are hundreds of formats of laser form. LiBLAST is another example you'll see in the literature. We use a very simple ASCII text file called PCD. And that's the file format that Point Cloud Library uses that I can show you in the demonstration. Routines need to be written. We're writing those routines. It's not a trivial task to assemble points which have no intelligence. It's just a cloud of points, and you have to find a way to algorithmically connect those points into information about whether that's a fruit of a plant or a leaf of a plant or a stem, or is it the soil. We're using Point Cloud Library for the routines, and for the visualization we use Cloud Compare. If you just take a slice out of the data, so as you're driving through, this is what you might see through a cotton crop, so it penetrates very nicely to the soil. This is the illustration. The LiDAR unit is mounted here. This is all noise up in here. You get profile of the canopy. If the canopy is very tall, it's brushing against the tractor, which is why it's chopped here. You can see the furrows in the beds here very clearly, and you can come up with some very simple density profiles here and plant heights as illustrated here. So that's a first order data analysis with LiDAR data. What you can do next is you can visualize with this Cloud Compare. These are some snapshots from Cotton Experiment from 2012. And these are a little hard to see on the screen, but you can rotate these around and you can see the furrows in the beds and the gaps in plants, plant spacing, where the leaves are denser and sparser. So we think that LiDAR will be, quote, the gold standard for canopy height and width. But it's a complicated instrument to implement. Use near infrared for your light sources. And then, of course, there's the eye safety issue. And I have a few references here, but the literature is vast on LiDAR. And that's it. Thanks. If there are any questions? Okay. Kelly, are you next? Oh, there was one question back there. Well, we don't have those numbers yet. Yeah, that's a very good question. So the question was how our bulb counts compare with the actual yield. We do have yield numbers tabulated. We have the bulb counts from selected rows. So we have that data. We just haven't analyzed it yet. Yes?
And you said it was after defoliation.
Yes. So I don't think you'd be able to resolve the bulbs if it's fully foliated. That's true. The question was, could I resolve the bulbs? We resolve those bulbs when it's defoliated. So I guess you could say it's an easy target, right? You can't see something if there's a leaf in front of you. And LiDAR isn't going to solve that problem. So if the photons can't penetrate the canopy, you're not going to see. It's not a magic device, not X-ray specs or anything. Any other questions?
Okay, good morning, everybody. Again, can you hear me? Okay. So I'm going to cover with you some of the basic physics of spectral reflectance from crop canopies and how we go about measuring that. I'm going to talk about electromagnetic radiation, the physics of light, paths that energy can take from the sun to the earth, to crop fields, and reflected back to our sensors. Spectral reflectance and what factors affect the reflectance of light from plant canopies, what sensors are available for measurement, how you calibrate those sensors, and how you analyze the data. Okay, so electromagnetic radiation, or light. We know from physics that light exhibits this characteristic called wave-particle duality, where the wave component describes how light moves. We know the speed of light is a constant, and this physical equation tells us that the frequency of the light, or the number of cycles of the wave per second, times the wavelength of light, or the distance between peaks of a light wave, is equal to the speed of light. But we also know that light interacts with matter, and when light does that, the energy of light can be measured as a photon. The equation for one photon, or one quantum energy, is a constant, Planck's constant, times the frequency of light. It's the basic introduction to the physics of light. Light can be classified into different wavelengths, and we typically refer to the electromagnetic spectrum as a way to classify different types of light. As human beings, we're most familiar with this one, visible light from 400 to 700 nanometers. Those are the wavelengths that our eye can detect. But for agricultural remote sensing, we are also interested in wavelengths a little bit longer than what we can see in the near infrared from 700 to 1,000 nanometers, and mid-IR or shortwave infrared on out to 2,500 nanometers. Thermal remote sensing happens out here. This is where Andy's talk focused on earlier in the morning. Thermal IR out at 10,000 nanometers. And you can see the other types of light. These things here are more harmful, and these we use often in our telecommunications. So for passive remote sensing, typically the source of light is, of course, the sun. The sun is the light source for most all passive remote sensing. So one characteristic of matter is that it all emits some form of radiation from it. And the amount can be described by the Stefan Boltzmann law, where essentially the radiance emitted from an object is equal to or proportional to the temperature of the object to the fourth power. So the sun is a very hot thing, and so it emits quite a bit of radiation. The emittance of radiation from objects varies with wavelength, and so we can say that there is a emittance spectrum from a given set of matter. The light emitted by the sun can be plotted here. So mostly you have light in the UV range, in the visible range, and infrared range that is being emitted from the sun. That light or that energy travels across space, and some of it begins to interact with the Earth's atmosphere. So when that happens, several things can happen to the energy. The gases in the atmosphere can scatter some of that energy back into space, either up or down. So that is what results in the sky that we see, is this scattered energy by the atmosphere. The atmosphere also absorbs some of that energy. The molecules of the gases in the atmosphere absorb some of the energy into the matter. And so the type of light that you or that is around you standing on the surface of the Earth is a very different characteristic than the light that you would receive sitting on top of the atmosphere. The atmosphere has an attenuation effect, and that effect differs with wavelength. So this would be the spectrum of light that would be received at the Earth's surface after it has interacted with the atmosphere. So you see many wavelengths are blocked, essentially, by the atmosphere. The bottom part of this plot shows different types of sensors that are available for detection. Of course, our human eye is one sensor. The sensors that we'll be discussing mostly in this workshop for detection of radiation from plant canopies are in this range, from the visible NIR portion of the spectrum on out to the thermal IR. Solar energy can take different paths. And so when you begin to work with remote sensing, with sensors, you always have to be mindful of the different paths that the energy can take on its way from the source of the light to the scene that you're attempting to measure, and then reflected to your sensor. We typically talk about two components of light that reach the Earth's surface. There's a direct component. This is energy that basically comes to the Earth, from the sun to the Earth, uninhibited by the atmosphere. And skylight is the portion of light that actually interacts with the molecules of the atmosphere, some of which can be reflected in all directions or emitted. So those are the two components of light coming from a source to a given scene. Then light can be reflected from that scene. Some of that reflected energy arrives at the sensor that we're measuring. But we have to be mindful of the fact that light is also interacting with the atmosphere and being reflected from molecules in the atmosphere that are not part of the scene that we're trying to measure. Likewise, if there are things next to the scene that we're measuring, so a tall building or something, well, light can interact with that building, reflect off the target into the sensor. So we have to be mindful of the different paths that radiation can take while we're in the field using our sensors. Okay, when energy is incident on a particular piece of matter, three things happen. Three possibilities can happen. A portion of the light is reflected away or scattered. A portion of it can be absorbed by the matter, and a portion of it can be transmitted through the material. So we have an example here of a pond where that would be the case. We have some incident energy from the sun. A proportion of that energy is reflected away from the surface of the pond. A portion of it is absorbed by the water molecules, and a portion of the energy is transmitted through the water and interacts with the underlying soil background. The same is true for a plant canopy. If you have a plant canopy, A portion of the radiation is reflected away from the leaves of the canopy. A portion of it is absorbed by the canopy and used for photosynthesis. And a portion of it is transmitted through the leaves, interacts with the underlying soil background in the same way. And a portion of that light is then absorbed and then reflected back through the canopy. So you have to keep in mind that when we're dealing with radiation and trying to measure it, that often it's a very fluid thing. It's not simply thinking of the top of the plant canopy as a surface or as a mirror, say, but in fact the radiation is interacting with the whole depth of the canopy and even the underlying soil background. Typically what we're measuring, though, is the percent of energy reflected. So we typically talk about percent reflectance. Percent of reflected energy is simply equal to the amount of reflected energy divided by the total incident energy. Surfaces reflect light differently depending on the characteristic of that surface. In the ideal case, we think of specular reflection. This would be like a mirror, okay, where the reflectance of light from that object obeys the law of reflectance, which says that the angle of incident light on that surface is equal to the angle of reflection from the surface. On the other side of the spectrum, we have a diffuse reflector, and these are typically more rough surfaces. In the ideal case, we talk about a Lambertian surface. And this would be the case where if you had an incident light beam on that surface, then that particular surface would reflect light equally in all directions. So it does not obey this law of reflectances. Typically, when we're dealing with plant canopies, we're somewhere in the middle, somewhere in here. There's a portion of the light that's being reflected that is a direct reflection from the canopy, and there is a portion that is a diffuse component. Spectral signatures is a term that's sometimes used to talk about the spectral response of different materials. I don't particularly like the term, but nonetheless, it's used because, generally speaking, it provides a way to sort of identify the type of surface that you're measuring reflectance from, because each type of surface or thing typically reflects with a different pattern. So a spectral signature is simply the reflectance of light versus the wavelength of light. For vegetative reflectance, we typically see this kind of pattern, from 400 to out to 2,500 nanometers. So why? Why does vegetation tend to reflect light that way? Basic reasons are that from 450 to 670 nanometers, this is where chlorophyll absorption happens. So leaves are made up of chlorophyll. Those chlorophyll molecules absorb a lot of radiation in those wavelengths for use in remote sensing or for photosynthesis. And so when you're doing remote sensing, then you're measuring the reflectance of light from that canopy. Then the reflection is low because most of the energy is going to absorption there. Contrasted with that is the near-infrared portion of the spectrum. That happens from about 700 nanometers out to 1,300 nanometers. So this goes beyond what your eye can detect. But plants have the property of readily scattering, readily reflecting light in those wavelengths. So if your eye could detect those wavelengths, plants would be very bright to you. And finally, out into the shortwave infrared or mid-IR, you see these depressions in the reflectance curve. That's due to the effect of water in the plant canopy. So at 1,400 nanometers, 1,900 nanometers, and 2,700 nanometers, we call them water absorption bands. So water has the effect of absorbing radiation in those wavelengths, and so when you're measuring the reflectance, you get a depression in reflectance. Soils also have a particular reflection spectrum, and typically they look like this. Okay, but the spectral reflectance from soil does vary, and many things can affect that, including the soil moisture, the soil texture, roughness of the soil, organic matter content, iron oxide content. And an important point to consider is that often in agricultural remote sensing, we're dealing with partial canopies. That would be a case where you have a crop that's halfway to canopy cover, and so you have a portion of the scene that's exposed soil, and you have a portion of the scene that is actual crop canopy. So this comes into play a lot more whenever we're using, say, UAVs or airborne remote sensing, and we're not getting images that resolve individual crop rows. We have to be mindful of the fact that the spectrums that we're measuring are, in fact, a combination of the soil and plant in the scene. When we're on the surface, or closer to the surface, what we call proximal sensing, it can still play a factor, and I have a few examples. For example, if you imagine a plant canopy, a row, say, going this way, and the sun is out here somewhere, and you have bare soil on this side. So if you take a spectrometer and you actually measure the reflection from this piece of soil here, you can often get somewhat of a vegetation spectral signature, and the reason is because, again, you have to be mindful of the travel path of the radiation. If the sun is over here, the light travels through that plant canopy, it is attenuated by that plant canopy, and then transmitted through to the soil near it, then this soil will kind of appear to have roughly a vegetative spectral reflection. Likewise, an issue that I encountered while collecting spectral measurements in cotton was a case where I had two cultivars right next to each other, and one cultivar only of cotton grew, say, 1 meter high. The cultivar in the adjacent row grew to 2 meters high. So, and the sun was to that way. So I'm trying to measure the reflectance from this shorter cotton canopy. Have to be aware of the fact that the light is traveling through this taller canopy before it is actually interacting with the canopy that I'm trying to measure. So some more about what kind of factors you have to be mindful of when collecting passive spectral reflectance data. Things that impact the measurements. The illumination angle is a factor, or the solar zenith angle. Solar zenith is essentially if you think of a vector from the top of your head straight up, and you think of the second vector to wherever the sun is, then that angle is the solar zenith angle. So at morning, at dawn, you have about 90 degrees, and depending on your latitude and time of year, you have a different solar zenith angle that's achieved each day. And you can imagine that as the sun rises and sets, that the light coming in to your plant canopy is different. And so that's going to impact how light is reflected. Similarly, the viewer angle. So you have the choice of positioning your sensor at different view angles. And depending on that choice, you will get a different reflectance response from your canopy. Typically we use nadir views, but it is possible to look at different view angles of light reflected from the canopy and get different responses. So collectively we call this the BRDF, or bidirectional reflectance distribution function. It's basically, if you think about all the different angles with which you could illuminate a scene and all the different angles with which you could measure reflectance from the scene, totally considering that together is the bidirectional reflectance distribution function. Solar trajectory, as I mentioned, affects the reflection from a crop canopy. This changes with time of year. I've plotted here the solar zenith angle for Maricopa at 4 times of the year, the equinoxes and solstices. And you see at the winter solstice, we're only achieving a solar zenith angle of about 65 degrees, whereas in the summer we get 10 degrees. So it varies. So that is an issue when you think about scheduling your field outings. Because if you tell your technician to go out and measure spectral reflectance from the canopy at 9 o'clock every morning, you have to be mindful of the fact that as the season progresses, the illumination angle on the canopy will change. And so that affects the BRDF that's at the canopy at that time. One of the ways that the BRDF affects canopy reflectance is through canopy shadowing. It depends on the solar zenith or illumination angle, but also depends on the leaf size and the orientation of the leaves in the canopy. You see an overhead photo of cotton. Given this shadow right here, I imagine the illumination is on this side of the photo. And you can see all the shadowing that is present in this side of the canopy. So that, of course, impacts how you measure reflectance from that canopy. Also, row direction. So if you have north-south facing rows, typically at solar noon, you won't see this shadow down the row. But if you had a east-west facing row, then for sure you would see that, and it would change with plant height. Other factors, cloud cover and particulate matter affect the amount of radiation that reach the crop canopy from the sun. And so often we try to target passive remote sensing to times where these are not a factor. It's easier to do in Arizona than most other parts of the country. Some people don't think about wind, but in the case you have a windy day and you go out with your sensor, you have to be mindful that the canopy is moving. And with that movement, the shadows are changing all the time as you're measuring reflectance from the canopy. So you just have to think of that. And if you have some odd data on that particular day, then maybe that's a reason. It was mentioned earlier, dew. If you go out first thing in the morning and you have dew on the leaves, that's going to affect the way that radiation interacts with your canopy and is reflected away. And finally, background materials. So whatever you have underneath the canopy itself, the color of the soil, the moisture level of the soil, different soil properties, and if you have crop residue or not, that changes the sort of background reflection from the soil, which can affect your reflectance measurements from the canopy. I'd like to shift now to provide some examples of different options for measuring canopy spectral reflectance. This is one of the first radiometers that was used and tested very heavily here when in the 80s, whenever some of these remote sensing concepts were first being developed. It's an exotech radiometer, basically collects information in 4 very broad wave bands. This was an analog instrument, so it output a voltage. It's a passive sensor, meaning it doesn't have its own light source. Mostly a sensor like this is obsolete for what we're doing today, but just due to the historical importance of the sensor, I included it here. Most folks today are using sensors like this. This was company ASD makes a field spectroradiometer. This is more of a hyperspectral radiometer, so it's measuring reflectance in a lot of narrow bands, over 2,100 narrow bands. This instrument is measuring reflectance. And you see that it covers the visible, even some in the UV, on out through the NIR and into the shortwave infrared wave bands. It's not a cheap thing. It's $65,000 for this instrument, so you can imagine getting pricey if you wanted to mount 4 of these on a tractor, and maybe you wouldn't want to risk putting that high-dollar instrument on the vehicle in the first place. So we've looked into these inexpensive, I'm supposed to say as an engineer, I was taught to say inexpensive and not cheap, but inexpensive spectroradiometers. These are Ocean Optics Jazz spectroradiometers that we've bought here locally. They collect information just in the visible and NIR, so you lose out on the mid-infrared bands with this system. One of the interesting characteristics of a system like this is that it's expandable, so you can attach between 1 and 8 independent spectrometers to the instrument. So that would give you some options for putting fiber optics at different angles or over different rows, or however you want to set it up. We bought a system with 4 spectrometers with some accessories for about 16 grand. Okay, so data from these sensors have to be calibrated. With the exception of the Exotech, we typically use digital spectroradiometers these days, and so the instruments record data as digital numbers. They're just integers with some bit depth that's associated with the instrument, and that's what the instrument provides you. But typically when we talk about spectral reflectance, we're interested in either radiance, which is a energy measurement per area, or percent reflectance. And there are a couple ways that you can get at these values. Laboratory procedures are used to calibrate instruments. These are often performed by the instrument manufacturer, and so you can have them do that for you. This is the quote from ASD on their procedure for calibrating their instruments. What this essentially does is it produces what I call a calibration file, and this would be just a list of numbers that you can multiply the data in the calibration file by the digital number measured by the instrument, and from that convert the dN to radiance at each wavelength. There are also field procedures, and typically these provide you percent reflectance and not radiance. Spectralon panels are a typical approach for obtaining spectral reflectance from field measurements. Spectralon is a material that's made by a company called LabSphere, and it's a material that was designed specifically for remote sensing applications because of its near Lambertian behavior. Remember, Lambertian means that surface reflects light equally in all directions. And so this panel is designed to reflect 99% of incoming radiation in a Lambertian form. One issue with them is that they have to be well maintained. We use them in the field, and so it can happen that they get dirty. They have to be clean. They have to be very well maintained so that they can keep this 99% reflectance, and you can calibrate your data accurately. Another approach is to use a cosine receptor mounted on an upward-looking spectrometer. So in this case, you would need 2 spectrometers. One would look up and one would look down. The upward one would essentially be giving you your incoming solar radiation, and the downward-looking one would provide the amount that's reflected back from the canopy, and from that you can get to percent reflectance. I'd like to move on now to options for analyzing spectral reflectance data. The most common and probably well-known approach is to use vegetation indices. And these were initially developed as broadband indices because it was, at that time, broader band instruments were being used, particularly in satellite remote sensing. Vegetation indices are essentially equations that use reflectance at specific wavelengths to calculate an index. And these indices have been correlated with many different characteristics of canopies, including the cover of vegetation. Some people say the greenness of the crop, the leaf area index, biomass, and even yield. The most popular one is the normalized difference vegetation index, or NDVI. It is simply calculated as the difference between NIR and red reflectance over the sum of those values. But even back 20 years ago now, there was a paper out that knew of 40 different indices that had been developed and tested. And so I think that's a problem that we run into with this kind of research, is that there are many, many, many different kinds of indices that have been developed, and the utility of each one may be questionable. To make things even more confusing, since we've moved on to hyperspectral systems with the capability of measuring reflectance in over 2100 wavebands, say, some researchers have used the NDVI equation and calculated the NDVI while considering all the different possible 2-band combinations from a hyperspectral instrument. So you can see what you can, if you do the number of potential combinations of two bands of 2151, you get over 2 million indices. And so what does that mean? What are those indices useful for? What are they correlated with? Sometimes remains an open question. With hyperspectral data, we are collecting a spectrum, and so that provides some other options for data analysis. Some researchers have used derivative indices, which use consecutive reflectance measurements in adjacent wave bands to calculate the first and second derivatives of reflectance. So if this is a standard reflection curve from, I think this was collected over a soybean canopy, this would be the first derivative of that canopy reflection. You can see this nice peak, which provides some information about what we call the red edge, or the rise of reflectance from where chlorophyll strongly absorbs red light to where the plant canopy actually scatters near infrared radiation. And here's the second derivative. Also, we have singular value decomposition methods, including principal component regression or partial least squares regression. And these are statistical procedures that aim to sort of condense or reduce the hyperspectral data into a set of reflectance, into a set of factors that aim to do two things. They maximize the variability in those factors, and they make sure that they're not correlated. So one of the issues with spectral reflectance data is that wave bands near to each other are often highly correlated, and so the question is, how much more useful information do you get from these measurements that are correlated? These approaches try to take the whole set of hyperspectral data and reduce them into a set of a few factors. Usually it ends up being like from 2 to 5 to maybe 10, depending on the data set. And then those factors can be regressed with different crop variables. We can also do physical modeling, and I'll get into this more later in the week. ProSail is a model of the physical interaction of light with plant canopies. It contains the prospect model, which is a model of how light is reflected from individual plant leaves. And it also contains the sail model, which is a model of canopy bidirectional reflectance, or how the reflectance of light from canopies changes with illumination and viewer geometry. The model takes as input several parameters, including information about the pigment content in the leaves, water content, different factors about the canopy architecture like the LAI, and information about the viewer geometry and illumination geometry. And the model then actually calculates the canopy bidirectional reflectance under all of those conditions. So this is an interesting way to link physical modeling with canopy spectral reflectance measurements. So for practical phenotyping and for practical applications in remote sensing, you've kind of heard of some of the struggles that we've faced with issues with illumination, angles, and cloud cover, and other things that affect passive remote sensing. And so engineers have designed these, what we call active sensors. The basic difference is that the active sensor provides its own light source. So there's an active light source within the instrument, and the instrument uses that light source and then measures reflectance in the wavelengths of that light source. So it tries to eliminate some of these issues with cloud cover, issues with time of day, and shadowing in the canopy. One of the limitations of the instruments is that to date they've only been developed for, say, 2 and 3 spectral bands. And so in terms of processing the data, in that case you're really limited to just using a simple vegetation index, and you can't get into some of the more complex spectral data analysis techniques that I mentioned. And so Pedro, I think, next is going to go into a lot more depth about active sensors. We have time for questions. You want to do questions or?
Questions for Kelly?
Man, I'm hitting a home run today.
Okay, can you hear me well back there? So my talk follows as Kelly set the background information on spectral sensors. So my talk is directed to the active sensors specifically. So as I'm going to present some material to you, some concepts that help explain how these sensors work. In the meantime, John is going to set up a quick demonstration of these sensors. So I want you to see some of those points that I'm going to make. Just you can see them visually with this demo that John will be working on. So let's get into the material. I'll be talking only from the conceptual point of view. I'm not talking in any engineering terms. I'm not interested really in presenting anything that's for engineering discussion, but more interested in presenting a concept that is complete, that is enough for you to see what's in these sensors. And I chose to use a material coming from a, let's see if I don't get it wrong. Okay, it comes from a patent, and probably this is not related to your field, but there was a lot of discussions on the merits of this patent and how it kept the development of this technology. But regardless of that, that was filed in 1995, and that kept developments from not happening because of the exclusive rights of this patent. But anyway, this patent was about using reflectance measurements from an active instrument to distinguish soil from a plant. And that seemed to be a very reasonable approach, and known for many, many years that the spectral response of soil is very different than that of a plant. Okay, so this patent is showing that they were looking at two wavelengths, two bands, 750 and 670 nanometers, and that was how they're going to use this sensor. So this is in the same patent. They're looking at a plant, and there is light being shined through to the plant in those two wavelengths, 670 and 750. With whatever electronics were here, some light was going to bounce back. It does bounces, reflects back, and then it's captured and measured, and the rest of the control system is here. So at this image, what I want you to see, it's mainly here. The fact that these light sources are modulated. So in this context, what we're talking about when we say modulation, it's just a manipulation of the signal so that it follows a predetermined format. In this case, it's a square waveform, and not only that, but it's delayed. So we know the magnitudes, or the system knows the magnitudes of those signals, and also knows the timing when those will be happening. The reason for this, why this is important, is that we need to separate the light. We want to relate that light that is reflected. We only want that light that was coming from these sources, so we can compute reflectance. But there's light from the sun, if this is used during the day, that will be also in that part of the spectrum. So we need to find a way to separate that and use only that light reflected that was emitted by these units here. Okay, so I want to acknowledge really the people that started working with this initially was at Oklahoma State University. And at this point, I also want to mention that the application is for variable rate fertilizer operations. Okay, so that set a lot of work in precision ag back then. I mean, 1996, 1997, they were really pioneers working on this technology. The point to make is that they were thought about sensors for farm management. Okay, and that hasn't changed that much. It's still sensors that are field ready, that in my opinion are good sensors for do phenotyping, and we have good data to show it. But at the same time, I want to be very clear. These are sensors developed for management of fertilizer applications. So they are not research-grade instruments. Okay. All right, so a couple of examples I want to show you. First, Holland Scientific. It's a manufacturer of crop circle. There are different models. We're going to show you one. This particular unit is an ACS 430 over here. And outside, we're going to show you calibration procedures for an ACS 470. But as I mentioned, this is meant to be a commercial unit for fertility management. So these are the sensors mounted on an application rig. And that's what takes the data real time and adjusts fertilizer rates. Another example is now Trimble that bought Entech. And then they have the green seeker type of sensor, which you see ahead over here, meant to be used in exactly the same context. Okay, so now let's take a look at some principles of operation, how we use this information here, or how we can obtain data that represents different vegetation conditions. Kelly already presented this graph. This is a part of the electromagnetic spectrum where you see the visible from 400 to about 700. So this is the region where our eyes can detect those changes, and the near infrared region here. So what you see there, these are curves developed with a passive unit, okay, 16 wavelengths, and the different curves correspond to different vegetation levels in cotton. So this is a project that I have with Sam Wang, who's around here, and we look at different plants, from plants that are just intact, they're not changed in any way, plants that are removed certain vegetation parts of it. Okay, so the amount of biomass is different for all those 5 different treatments. Okay, and as it makes sense to see, this is the plant that has no leaves being removed from the plants that are heavily changed in their biomass because vegetation branches are removed. Okay, so again, this is passive. This is a snapshot of the spectral response of those plants. What the active sensors do, I will repeat this and a couple of slides more, is to look only at 2 parts of the spectrum, the 670, and it can be different values here, but around 780 it will be a good point to look. Okay, so notice at this point, at this portion especially, there is very good differentiation of those treatments. Okay, so yes, you can have these curves developed, but the point here is with limited amount of data, can you still characterize these differences in vegetation? So I'll explain that more. This also came from a paper recently published, and what they're looking at, the reason I'm using this diagram here is only to point to the light source being produced here. We're using polychromatic LED and LEDs, and then reflection happens this way. Okay, so the main message for this slide is to tell you that light is modulated, produced at this light source on a particular part of the spectrum. Okay, and that's the same light that we want to record. So it's just to re-emphasize the point that I made already. The rest, it's electronics, okay? And those are, for the most part, we don't have control over those. Why there was this patent and this litigation happening? A lot of that was to do that we couldn't tap into these systems with the electronics that we had, okay? So we are limited. That's what I'm trying to say. We are limited, even as engineers. There's so much we can do on a product that's already being developed, okay? And one particular sensor, we have no way to know the raw signals. All we have is NDVI output. We'll get into that with more detail when we do the exercise B this afternoon. Okay, and to also reemphasize the fact of the concept of the light modulation technique, it's the fact that light is emitted at certain waveforms and at certain magnitudes too. This is known by the system. This is purposely emitted in this form. And then what light bounces back, hits the vegetation and then bounces back, it follows this waveform. And there is a time delay. In the horizontal axis of this graph is not listed there, but it's time. Okay? So they are offset. So the system is looking for a signal of a particular magnitude and happening at a particular time. That's how active spectral works. Okay? And that's how it can separate light from the same waveband, but just happening naturally by sun natural illumination. Okay, so quick view on what are those areas where we want to select as we are shopping around for sensors. What are those things that we can still look in the data sheets and have a better idea what they mean? First, on the light source end of it. So we, by now, use more than anything LED illumination. And this is one example that you're going to see with that setup over here. Those can be either polychromatic or monochromatic. Okay? That's just different manufacturers do things differently. On the receiving side, on the part of the sensor where it's registering data, light bouncing, reflecting back, we have photodetectors, and we have silicon photodiodes of this range. This is a good point to tell you that even though this is theoretically the limit of those photodiodes, with these active sensors, you certainly cannot go this much into the spectrum. They're not built for that level. Okay? So there's a range where you have very good data. But don't think that you can do any filter and reach any value, even within that limit. The filter itself can be a good option, but not the electronics of the system. And and filters are then characterized by wavelength and bandwidth too. Okay, so there can be very good filters, but if the bandwidth is too wide, then it's going to be integrating data over a larger part of the spectrum. So be aware of that too. If that's enough for you, well, that's fine. But if you are after a particular index, certainly not NDVI, but a index that requires a very, very narrow part of the spectrum, you want to look for a filter that can give you that in a narrow bandwidth. Okay, so I'm now moving into the use of these systems in the field, and that's John driving our first vehicle that we developed for this type of applications. Okay, so again, this is the working cotton that Sam Wong and myself did. Okay, so by now I show you these passive reflectance type of functions, and we look at two parts of the spectrum to compute NDVI. Kelly already defined what NDVI is. Now, what I'm looking here is that these happen on a particular day, which is this day. Now, we're looking at days after planting. So notice how using active sensors, they can differentiate between those treatments. Okay? That's the value of these units. With all the limitations that there is, and there are plenty of limitations, they can be very good tools for differentiating between plants of different vegetation characteristics. Okay, so these are the plants that have not been removed of any leaves. These are the ones that were severely treated, very aggressively removed some of the
leaves. Okay, so bottom line here is that if this is enough differentiation for me, I can use an active system in this research. Okay, now I want to get into an area where there is a lot of discussion, and that's on the effect of distance from the target. There's a tremendous effect, and there's tremendous aspects to discuss this issue. So I'm using this paper published last year, where they compared two sensors, the green seeker and the crop circle 470. So what they're showing here is with this particular index, which is sort of an NDVI version, you see that as the distance increases, there's only a small portion of the distance range where things sort of remain stable, and then the signal just goes high, really unreliable. And also for very short distances, we have a very erratic behavior here. That's green seeker. Crop circle seems to have a better response to that distance effect. Okay, so now on temperature, I'm looking here at the same index created here, and then green seeker and crop circle sensors compared. So when we look at device temperature, that's not ambient temperature, but the actual temperature that those sensors reach when they are using the field. For us in Arizona, it is an issue. Okay, it's a lot of radiation happening. So you see here that there's clearly a temperature effect. There's the slope of this line is significant for the green seeker, and then here is for the crop circle, a more stable, but still there's a slope here. And in this data set, you see that 40 centimeters away from the target, or 80, there's actually a difference between those two. Okay, so again, this graph actually tells you two effects: distance away from target and temperature effects. So these are things you need to be aware that will affect your readings. Okay, so I want to briefly touch on an aspect that will be developed more on the canopy architecture. So in this case, where we're looking at the effect of water stress in Pima cotton, this is work with Mike Gore that we did in 2012. What I'm presenting here is only the basic observations of NDVI. So we're looking at 12 plots. It really doesn't matter which ones are these. It's just, 11. 11 different plots with Pima cotton. And we're looking at plants that were water stressed and how different is NDVI at 7 in the morning than at 1 p.m. on August 12th day. Very, very hot, easily 112 degrees. I don't know what it was at that day, but it's really hot over here in August. So if we look at now well-watered plants, the differences between early in the morning to late in the day are minimum. And the main difference here is actually a change in leaf angle. These plants are changing, and they look droopy if you go outside. So here's one other factor that you also need to be aware of. Whatever it is that you're measuring, if you are using an active sensor, you need to be aware that there might be things that relate to the leaf angles and architectural changes, and not necessarily on how green or how big is the plant. Okay, so I'm kind of getting to a point summarizing some of the points of my talk, and want to re-emphasize here. Active spectral sensors are not research-grade instruments, okay? They were built with fertility management functions in time, and that was the purpose. And there's two main brands available in the US, Crop Circle and Green Seeker. So one distinction between those two is that with the 470, we have 3 wavelengths, and we can select which filters to use. And that brings a very good, very desirable situation that you can still select for certain filters. And the 430 is a lower cost version, but in this case, those wavelengths are fixed. I cannot change those. Okay? But here's one that I really like to make emphasis on. The output, it's in 3 channels, and I can log that data independently. So raw information I can collect. That way, that means that I can then compute other indices beyond NDVI sensors. And that's what we're going to see in a moment. Okay? So green seeker, only 2 fixed wavelengths. I have no control over that. And output, only NDVI. Okay? So in Europe, I've seen reports of using this JARA N sensor, but I have no experience with that. But I'm just pointing that. Okay, and really quickly, how we integrate this in a multiple row configuration. This is work of John Hyun, and he's using the system works on a RS-485 network, so it's just cascading, so we can have even more than 4 if we want to. And then there's GPS information coming in to the GeoScout data logger, which is a piece that goes along with the 470. It's a Holland scientific instrument. The reason is that these are being tweaked in a way that I cannot send those signals directly to my data logger. Okay? It's just one way that they protected their product. They're smart enough to develop these communication protocols that are slightly different. What's the difference? I don't know. They keep it secret, so I have to have their systems here. Okay? Be aware of that. Okay, so I'm finishing my talk. What I want to go next is to do a demo. We're going to dim the lights here in this section of the room and try to look at the signal coming from this sensor as it shines light into these plants. Are we good, John? Okay, so what we have here, as John gets ready, we have the ACS 430 sensor. These are corn plants. From where you're sitting right now, can you see the light on these plants? Feel free to move a little or just go on. I really want you to see that light here. Alternatively, what you can do is look at down here and see the light that is coming out of this sensor. That's the active light component of it. Yes?
When you switch out for different filters on like the ACS 470, do you have to have a different illumination source, or is it the same illumination source?
The question was, if I change different filters, do I need to change also the illumination? Within certain limits, no, you don't have to do anything. Good question, yeah. Okay, so if you guys can see that, that's the setting. These are plants, in this case corn. We have the sensor here. Now we're going to look at the output coming from that sensor. So bear with me. Just give me 1 minute to get this. So I'm going to switch. I'm going to project now the data coming off that sensor. All right, John, so. Right. Okay, so this is happening as we are talking. As I'm talking, I'm sorry. This is the raw data generated by this sensor. There's a purpose for me to show you this data in this format. And just to tell you, that's what you're going to get. Then you need to take these strings of data, which is serial communication. You need to take that into your data logger. You need to know which column is which. There is no headings in this case, of course. These are packets of information They do not contain labels. Okay? So you need to know which number is which. It's in your notes. The manufacturer provides you with that correspondence. Okay? So very clearly, I'm telling you, you need to read your data sheets or specs to come with whatever sensor you select to use. Okay? So you notice here, you don't know this, but the last column is NDVI. Okay? So it's about 0.4 fluctuating, I'm sorry, 0.5 fluctuating plus minus 0.02%. But look at how sensitive are these units. I'm just passing this piece of vegetation. As I do that, look at the output, how it changes. Okay? Is it changing now? Yeah. Very much. What if it's not changing? So this is the end of my talk. Really, but point to make this demonstrating with this other piece of plant material is how sensitive these sensors can be. Okay, it is a challenge that you use them properly, or the best that you can adapt them to your application. But you can have very good data coming out of these systems. Okay, be aware of the limitations. Work with your technical people on how you log this data, how you filter it if you need to filter it. But they're very sensitive, so they're very good tools if you can set that up in your phenotyping measurements. Any question at this point? We are just right on time to finish my talk, but if there's one or two questions, maybe I can.
I had a question on the graph you showed a few seconds before we went into the demo, where we had the irrigated versus the water stress at the 2 times a day. Would you also have issues with the near-infrared attenuating at different cell water statuses?
You repeat the question,
Yes. The way I understand his question is that when we're looking at 2 measurements done at 2 different times of the day, like very big differences I'm showing, then will I expect, correct me if I'm wrong, but will I expect to have a larger effect on the near-infrared than it is on the visible? Is that more or less?
Yes.
Well, maybe Andy can help me with that. I would say yes. I would say that's the part that is changing the most. You know, magnitude-wise, near-infrared has a much larger value than it is on the visible side. So I will say yes. That's mainly what you are, or a big portion of what the effect is happening. A good way to prove it is to have a spectral radiometer and then look at those 2 signals. Yeah. But good point. You know, guys, at the end, what I'm trying to encourage you as you move into applying these systems to your programs is to test things. Don't believe what people suggest to do. Just do your own testing. That will be a very quick validation of what I said. Did I answer your question?
Somewhat. I might clarify a little later. I'll talk to you after this.
There was a question back here.
Yeah. Maybe I'll get the mic. Thanks. How effective is the square form wave method in reducing the effective ambient light out there? Is there no effective ambient light with these sensors, or is there some?
It's very effective. Yeah, that's been perfected over time. Yeah, it is really good. You can really, that's an area where you have no uncertainty. Yeah. Yeah, naturally that light doesn't follow that form. It's manipulated that way. So magnitude and timing is really good. Yeah, go ahead. There's a microphone next to you.
May I not use it? I feel nervous when I use it. Okay. So back to your prod, that prod that you just talked about. Yeah, okay. Because I think, okay, when you did like the experiment in the different time, even like, in the morning or late afternoon.
Yes.
But I was thinking about the interaction between, okay, if the prod, different prods show the different varieties of maize or whatever, but okay, there's a difference between different time, but I don't know if there's an interaction between the varieties, but if that is non-significant, so maybe should we concern of that?
it's beyond my expertise to look at those effects coming, or those effects coming from the interaction of the plant itself. You know, I attempted to present here what I can see from the engineering point of view on how you can generate signals that differentiate different conditions. I will say to that point is you need to do your homework and make sure that those factors, you know which ones are they, and perhaps you can control for some of those interactions. But being aware that there are interactions, that's absolutely correct, how you can control them. That will be a question for your partners on the plant science part. Guys, it's 12:35. Lunch is ready now. I'll stick around for the rest of the day and, of course, the workshop. So if there's any other questions, something that you want to touch base with me, I'll be around. Yes?
Can you leave this running for a while?
Oh, we can do it, yeah. We'll leave it here. You can come and play with it. It's fine.
And the only announcement we have is that the vegetarian option is in the back, and non-veggie is against the wall over here. So lunch is served, and we will reconvene, I think, at 1:30. Okay, thanks.
Thank you, guys.